Hello and welcome. Ansys Fluent is a powerful and versatile CFD software which is widely used in industry and academia. Engineers are interested in using CFD simulations to test their ideas and analyze how they perform against numerous variables. Usually, this results in a large number of complex simulations which consume enormous amounts of time. It is imperative to have these simulation times reduced because ultimately this will reduce the time to the market. The traditional approach to reduce the simulation time is to increase the number of CPUs. However, the more recent approach is to leverage the power of graphics processing unit (GPU) to increase the simulation speeds without compromising the accuracy. Ansys has been a trailblazer in the use of GPU technology for simulation, and it is taken to a new level with the release of the multi-GPU solver in Ansys Fluent. In this video lesson, through a simulation example of an external aerodynamics of a DrivAer car, we will highlight the solver features available on multi-GPU solver. We will also see the power of GPU and how well it performs when compared to CPU for running CFD simulations. Excited? Let's get started. In automotive industry, external aerodynamic simulations can become very large, usually exceeding 300 million cells. These simulations would require thousands of CPU cores and multiple days of compute time, even weeks. An alternative to traditional CPU computing is by using GPU. GPUs are well suited for parallel computing since they can perform many calculations simultaneously and process large amounts of data much quicker than CPUs. Leveraging GPUs in the CFD world is not a new concept, and GPUs have been used as CFD accelerators for quite some time. Ansys Fluent implemented offloading to GPUs technology in 2014 by passing some parts of the CFD solver algorithm to GPUs to accelerate the overall solution time. The local acceleration obtained was case dependent, and as the Ansys Fluent solver was not yet optimized for GPUs, this limited the overall solution speed up. Starting with 2022 R1, Ansys Fluent takes this usage of GPU technology to a new level with the introduction of a new native multi-GPU Fluent solver. This new solver has been architected from the ground up to run natively on GPUs and exploit their full potential. This eliminates the overhead of exchanging data between CPU and GPU, hence resulting in faster simulation compared to offloading. Native GPU implementation results in astounding gains, and the main benefits include increased performance, reduced hardware costs, reduced power consumption. The multi-GPU solver supports all mesh types and is available for all incompressible and subsonic compressible flows. It also supports temperature-dependent material property definition as well as turbulence models, solid conduction, conjugate heat transfer, moving walls, species transport, and porous media. In this video, I will highlight some of the solver features supported by multi-GPU in the 2023 R1 version of Ansys Fluent through a transient simulation of external aerodynamics of DrivAer car. In this video tutorial, I will be simulating the external airflow over a sedan-type car. The mesh is comprised of about 13 million cells and includes an enclosure that will serve as the surrounding environment of the car. To make the simulation more realistic, the boundary conditions will be set such that the car is our frame of reference. This means that if we were sitting in a car moving at a constant velocity, we would see a flow of air with a constant velocity coming towards us, and the road would appear to move away. These are the boundary conditions we will be working with. We will explore the workflow of the native GPU solver and learn about its features and limitations throughout the process. Before commencing the simulation, I will provide a brief overview of the process I will be following. Our objective is to obtain an accurate transient solution using the SBES model along with the generating appropriate animation files for analyzing the results. To achieve this, I will carry out the simulation in 3 stages. First, I will obtain the steady-state solution, which will act as initial solution for the subsequent transient simulation. Then, I will run the transient simulation for a certain number of time steps to purge those initial transients that may exist in the solution variables such as drag force. Once the simulation reaches a statistically steady state, I will run more time steps to capture files for creating animation. To begin, I will open the 2023 R1 version Fluent launcher and select the solution mode. The Fluent GPU solver is only available at the enterprise licensing level. Once enterprise from the capability level drop-down list is selected, the native GPU solver option is activated under the solver options. To enable the GPU solver, I will simply check the native GPU solver option and click OK on the pop-up message displayed. Note that Fluent GPU solver only supports NVIDIA GPUs which are compatible with CUDA version 11 or newer. If your machine has a graphics card with more than one GPU and you intend to use the solver with multiple GPUs, then you will have to set the number of GPUs you want to use. In this case, I only have one GPU available. When using Fluent GPU solver, the CPU processes are only used for case setup and post-processing, while the solver calculations are done by the GPU. You can increase the number of CPU processors to use multiple CPU processors in parallel during case setup and post-processing. Please note that the number of CPU processors specified must be greater than or equal to the number of GPUs specified. After setting up the Fluent launcher appropriately with all the inputs, I will click Start to open the Ansys Fluent GPU solver. Although the graphical user interface of the Fluent GPU solver is similar to that of the CPU solver, it is important to note that Fluent features not supported by the GPU solver will not be available in the GUI. Next, I will load the mesh file by going to File, Read and selecting the mesh file. To display the mesh, I will go to Display in the Mesh group of Domain tab and click on Display after selecting all surfaces. Notice in the solver settings that only the pressure-based type of solver and absolute velocity formulation are available in the GPU solver. However, we can solve both steady and transient simulation in GPU solver. I will select steady as I will first obtain the steady state solution and then use it to initialize the transient run. To set up the physics of the problem, I will move to the Physics tab. In the Models group, we can see that GPU solver supports modeling of heat transfer, turbulence, and species transport without reactions. The other models have been grayed out as they are currently not supported by the GPU solver. To specify the turbulence model, I will click on Viscous. The turbulence models available to choose from are laminar, K-epsilon, K-omega SST, K-omega Gecko, and large eddy simulation. I will select the K-omega Gecko model and click OK. Moving forward, let's talk about the material definition. Since air is the only material required in this simulation, I will not define any new materials as air is available by default. The Properties section of the Create Edit Materials dialog box has options to modify the properties of the materials. The drop-down list will list the settings that are supported by the Fluent GPU solver. Currently, the property definition settings available in a GPU solver are fewer in comparison to those available in a CPU-driven solver. Now, I will proceed to define the boundary conditions. I will group the boundary surfaces by zones in the toggle tree view. For the inlet surface, the velocity magnitude will be set to 30 meter per second. While for the outlet, I will use pressure outlet type boundary condition with 0 gauge pressure. All the walls except the wheels and the ground will be defined as stationary wall with no slip boundary condition. For ground wall, I will assign moving wall condition. I will set the translational speed to 30 meter per second in the positive x direction. Next, I will define boundary conditions for the wheels. First, I will open the wall boundary condition for wheel FL and select moving wall. I will select rotational motion for this wheel and enter the values for rotation axis origin. I will also have to set the rotational velocity and rotation axis direction. The rotational velocity has been calculated based on the speed of the car, that is 30 meter per second, and the radius of the wheel, that is 318.4751 mm. The boundary conditions for the other wheels are set up in a similar way using the values shown. To know more about the boundary condition settings supported by Fluent GPU Solver, please refer to the user's guide. Once the physics has been set up, I will move on to the solution tab. In the solution methods task page, I will retain the default simple pressure velocity coupling scheme. Currently, only simple and simple C pressure velocity coupling schemes are supported by the GPU solver. Additionally, the GPU solver does not currently support the pseudo time method. Now, to monitor the solution, I'll create a report definition for the car's overall drag. For that, I will go to Definitions, New, Force Report, Drag, and choose all zones other than ground moving, which implies all the surfaces of the car are chosen. Choose Drag Force from the Report Output Type option. Checking the per zone box, I will obtain the iterations versus drag plot for each surface. I will keep the report file and report plot boxes checked and click OK. I will initialize the solution using the standard method. Please note that GPU Solver supports both hybrid and standard initialization. I will enter 2000 for number of iterations input and save this case and data before running the simulation. This simulation was run on a multi-GPU server to speed up the simulation. Here is the drag plot we obtained. It clearly shows that the estimated drag force has stabilized after the initial iterations, indicating convergence. Now that I am done with the steady part of the simulation, I will move on to setting up the transient simulation. For that, I will first change the selection from steady to transient in the general task page. Then in the viscous model dialog box, I will retain the k-omega GECO model and check the SBES under scale resolving simulation options. GPU Solver supports LES, SBES and URANS simulations. Then in solution methods, I will change the transient formulation from first order implicit to second order implicit. The time step size used is such that the cell convective coherent number is less than 1 in regions where turbulence in the computational domain is resolved. In this case, it is mainly in the wake region of the car. For the first stage of transient analysis, I will solve for 100 time steps to ensure any initial transients is cleared out. Also, I will set the max iterations per time step to 30 in the run calculation task page. Once I have obtained this transient SBES solution, I can now set up the animations. I will create an isosurface for Q criterion normalized. For that, in Results tab, I will go to Create Isosurface. Select Velocity from Surface of Constant drop-down menu and Q criterion normalized from the second drop-down menu. Select Tunnel from Zones and click Compute. Now I will create an isosurface for a value of 500. Moving further, I will go to Contour, New to create a contour of vorticity magnitude. For that, I will select Velocity from Contour of drop-down menu and Vorticity magnitude from second drop-down menu. Now we will select Q Criterion Normalized 500 as the surface. Uncheck Global Range, Auto Range and Clip to Range. Set the minimum value to 30 per second and maximum value to 5500 per second. I will uncheck the Show Color Map option so that it is not captured in the animation. Now you can see the contour on the graphics window. Similarly, I will create a velocity contour. I will skim through the steps quickly as they are similar to what I did previously. The new contour of velocity magnitude is created on the plane XZ surface with maximum limit of 50 meter per second. The velocity contour is visible in the graphics window. The large wake region behind the car can be easily noticed. Now that we have vorticity and velocity contours, we can make two scenes for them. To begin, I will create a mesh display object by going to Mesh, Create and selecting all the wall surfaces. Now let's apply materials or colors to the surfaces. Choose By Surface under Coloring. Here I will assign materials or colors to the car, all the four wheels and the ground to get the desired visual appearance of the model in the animations. I will name it as Car Mesh and save it. The mesh object is now complete. Further, I will create two scenes by combining the mesh object with each contour which will be used in the animations. To create the first scene, I will right click Scene in the outline view and go to New and select Car Mesh and Velocity. This scene will be saved every specified time step to be later used to generate the animations. Similarly, the second scene will be created by the combination of vorticity and car mesh. I will also set up the views for the animations. For that, I will first display the velocity contour scene by right-clicking and saying Display in the outline view. Now for this, I prefer the view that is normal to the plane. So, accordingly, I will save this view as Velocity View. And then similarly, I can set up a suitable view for our vorticity contour scene and name it as Vorticity View. Now that we have set up our scenes and views, let's proceed to set up the required solution and animations. To do this, I will first navigate to the outline view and then select the solution option and then calculation activities. Right click on solution animations and select new. Next, I'll choose velocity contour as the animation object and velocity view as the animation view. I need to specify a storage directory where I want to save the animation files. I want to record animation frames after every 6 time steps. I will repeat the same process for the vorticity magnitude animation. I will select vorticity contour as the animation object and vorticity view as the animation view. Set the record after every value to 6, choose a storage directory and that's it. Now that everything is set up, I'll save the case and data files at this stage. For running the calculation, I will set the number of steps to 300 and hit calculate. After the solution is calculated, now it is the time to write the animation into the video format. For that, I will go to the playback animation under the outline view and click read and load the .cxa file for velocity animation from the storage directory where the animation files are stored. From the Write Record Format drop-down menu, I will select video file and set the resolution to 1920 by 1080. I will click write and Fluent will start to write the video. The animation video for the vorticity contour can be created in the same fashion, and this is how the animation videos look like. Now that we have successfully completed the simulation with desired results, let me show you some comparisons when this simulation is running on different processors. The displayed bar chart is a comparison between speed of the simulation when compared on different CPU and GPU configurations. Taking Intel Xeon Platinum 8380 CPU with 80 cores as a reference, you can see how significant the rise in speed is when it comes to GPU. A single NVIDIA A180GB GPU can be nearly 5 times faster than a cluster with 128 AMD EPYC 7763. This is a quantitative proof of GPUs being extraordinarily faster than even large number of cores of CPU. The power consumption is another important factor to consider when comparing GPU servers and CPU clusters. A chart comparing the power consumption of both approaches shows that GPUs consume significantly less power than CPUs, primarily because they solve faster and hence run for a shorter amount of time. In this particular case, the power consumption of the GPU server was almost 4 times lower than an equivalent CPU cluster. This lower power consumption results in lower simulation costs for GPUs, making native GPU solver an economical and faster solution for industries. Let's summarize the video. In this video, the capability of the native GPU solver of Ansys Fluent to solve external aerodynamic problems in the automotive sector was demonstrated. GPU solver has significant benefits over CPU-driven solver, which includes substantial reduction in simulation times and hardware costs. Using the simulation example, we learned about the Fluent features supported by the GPU solver. More and more features will be supported by the GPU solver in future releases. Thank you for watching and happy simulating.